electrophilic substitution and free radical addition of benzene. I told you the mechanism of electrophilic substitution, where first the electrophile attacks the benzene pi ring and makes a 4-valent carbocation intermediate. I told you why this is called 4-valent, because the carbon has 4 bonds, yes, and is sp3 hybridized. Then the next step, there is expulsion of H as H plus, and the pi ring is reformed. This happens in 2 steps, therefore you will see 2 bumps in the energy profile diagram. Then I told you that prior to substitution, you got to make the electrophile in the presence of a catalyst. So chlorine plus AlCl3, that needs to be anhydrous, because if you take it with water, AlCl3 will hydrolyze. So this is the catalyst, and they first make the electrophile, that is Cl plus, by this reaction right here. And then electrophilic substitution will continue, and you will get chlorobenzene as the product, HCl as one of the product. How do we get HCl? The H that is expelled as H plus along with the Cl minus over here will make HCl, and the AlCl3 catalyst is regenerated. So this is the reaction mechanism for electrophilic substitution. We saw chlorination yesterday. I asked you guys to do bromination as homework, right? So let's see the reaction, the bromination reaction as of electrophilic substitution. So you have the reactant. The reactant is bromine liquid, not bromine aqueous, because if you take bromine water, then the catalyst will break, right? And what will be the catalyst? The catalyst would be AlBr3. You can also take, by the way, FeBr3. Yes, so you can take FeBr3 or AlBr3. So that will be your catalyst. Now let's just see the overall reaction first. So the overall reaction for bromination would be benzene ring reacting with bromine in the presence of AlBr3 to give bromobenzene, plus HBr. That'll give you steamy fumes. Yes, and this bromine needs to be what? Liquid. Now let's see the generation of electrophile. So how will you generate the electrophile? That is going to be prior to electrophilic substitution. So generating the electrophile. Yeah, so let's see how we do that. So you have bromine plus AlBr3 making AlBr4 minus plus Br plus. So you have Br right here. Yes, this with AlBr3. Now what happens is that this undergoes heterolytic fission such that both the electrons go to the same Br. So let's go here. There will be a lone pair here. Since it gains an electron, this will be negative, this will be positive. And this makes a dative bond with the Al here, because Al has a vacant orbital. And what will you make? You will make AlBr4 minus. Yes, so you make AlBr4 minus plus Br plus. Yeah, so once you've made this, now let's see step 1 of electrophilic substitution. So in step 1, what will happen? We will have benzene ring, and that will react with the Br electrophile. There will be an arrow from within the ring to the electrophile like this, and you will make a 4-valent carbocation intermediate. Yes, and the Br attaches here, and you have the H over here. Then in the second step, let's see what happens in step 2. In the second step, you have the 4-valent carbocation intermediate. So you have this Br and H, and this will break and it'll be expelled as H plus. So this goes back in the ring, reforms the pi ring. Along with AlBr4 minus, you will get your product, which would be bromobenzene. So you have bromobenzene as one of the products, and the H plus that is expelled with Br minus will make HBr, and AlBr3 will be regenerated. Clear? So that is step number 2. And you see that this is regenerated. And that's what a catalyst should do. It should be unchanged, should be regenerated. Clear? So this is halogenation. We saw chlorination, and this right here was bromination. Clear? So we have chlorination and we just saw bromination. So we've seen halogenation of electrophilic substitution. Now let's see nitration. The next one is nitration. So let's see nitration now. So let's see nitration. Now you can have two types. You can have mononitration and you can have dinitration. So in mononitration, you will just have one nitro group attaching, and you can have dinitration in which you will have two nitro groups attaching or substituting to the benzene ring. Now let's see the reagent. The reagent for mononitration would be concentrated nitric acid. So you have concentrated HNO3. And what will be the condition? The condition would be H2SO4 catalyst. So you have sulfuric acid as catalyst at 55 degrees Celsius. So these are the conditions and the reagents for mononitration. For dinitration, the reagent is the same. You have concentrated nitric acid. The conditions, however, are slightly different, which is in terms of temperature. So the condition is that you need sulfuric acid as catalyst, and this is at temperatures above 60 degrees Celsius. Clear? Now the electrophile that you make during nitration is NO2 plus. So the electrophile is NO2 plus, right? We call this what? The nitronium ion. What do we call this? We call it the nitronium ion. So this right here is the nitronium ion. Now let's see the overall reaction. So let's see the overall reaction of mononitration. So let's see mononitration first. Now you have benzene ring, that is C6H6. This will react with HNO3 in the presence of H2SO4 at 55 degrees Celsius. Yes, because mononitration occurs at 55 degrees Celsius, giving you C6H5NO2 plus H2O. Let me show you the split formulae. So you have benzene right here, this reacting with HNO3 in the presence of H2SO4 catalyst at 55 degrees Celsius, giving you nitrobenzene as the product and H2O. So this right here is what? Nitrobenzene, right? And you see, this is what? This is mononitration. You just have one nitro group attached to benzene. This nitrobenzene is yellow oil. So it's like yellow in color. So it's like a yellow oil. So your observation will be that a yellow oil is formed. Now let's see the mechanism. So for the mechanism, the first thing you need to do is generate the electrophile. So mechanism for mononitration. So let's see. So mechanism of mononitration. So this would be, first step would be to generate the electrophile. So to generate the electrophile, what is our electrophile? NO2 plus, right? And this electrophile is produced in the presence of a catalyst. And we know what that catalyst is, sulfuric acid. Yes, so this happens in the presence of a catalyst. So you have two H2SO4, that's the catalyst, with HNO3, that's nitric acid, that's the reagent, giving you 2HSO4 minus plus NO2 plus plus H3O plus. Now let me explain this. So we have these two reactants. If you see H2SO4, this is an acid, right? So this is an acid, that means it will be a proton donor. And do you see that? Do you see it is donating its proton and becoming HSO4 minus? From H2, it is becoming HSO4 minus. Yeah. So this is a proton donor, which is an acid, and it is also the catalyst. If you look at HNO3, technically that is also an acid. But if you see, HNO3 is releasing the OH. Do you see? You have if I remove H and O from this, we will be left with NO2. Do you see HNO3 releases the OH and it becomes what? NO2 plus. So this releases the OH. Yeah. So if this releases the OH, this would be what? The base. Do you see it releases the OH and makes the electrophile, that is NO2 plus. So it loses the OH minus. So from HNO3, if you remove H and O, yeah, so this will become, so you've removed OH minus, so you will be left with NO2 plus. So you remove OH minus, and you will be left with NO2 plus. And that's how we get this NO2 plus electrophile. Now the OH minus, along with the H lost with this, yeah, so you have the OH minus and you have two hydrogens, right? So you will make what? H3O plus over here. Now if you see, this is balanced because you have 4 hydrogens over here and 1 5, and this is 2 3 4 5. You have 2 sulfurs. You have 2 4s are 8 oxygens here, and 8 plus 3 is 11. So you have 8, 9, 10, 11. Oxygen is also balanced. Yeah. Nitrogen is also balanced. Everything else is balanced. So this is how we make the electrophile. H2SO4 loses a proton, HNO3 loses OH, and you get your electrophile 2HSO4 minus and H3O plus. Now we've generated the electrophile. Let's see the mechanism now. So let's see the mechanism. Let's see step number 1. In step number 1, we have the benzene ring with the nitro group. Yes, with the nitro electrophile. You'll show an arrow from within the ring to the electrophile, and you will form a 4-valent carbocation intermediate. So you have a 4-valent carbocation intermediate. Clear? What is step number 2? In step 2, this 4-valent carbocation intermediate will release the H as H plus. So this is the NO2, this is the H. So this H is expelled as H plus. Both the electrons, you reform the ring. Yeah. Now what else did we have here in the product? HSO4 minus. So we take the HSO4 minus because the catalyst needs to be regenerated. So the H plus with the HSO4 minus will become H2SO4. Yes, so it will reform the catalyst. Do you see H2SO4 is regenerated? Clear? So you have H2SO4, this is regenerated. And what is our product? It is the yellow oil of nitrobenzene. And do you see there's only one nitro group attached? Therefore, we call this what? Mononitration. Is this clear? Do you guys understand? Now, this was mononitration, and this was happening at 55 degrees Celsius. However, if you increase the temperature, if you make it more than 60, the if you increase the temperature more than 60, then it will undergo dinitration, right? So let's see. So if you have a nitro group already attached, so if you have NO2, this with HNO3 in the presence of sulfuric acid as catalyst at a temperature greater than 60 degrees Celsius will cause dinitration. So this results in dinitration. You will have NO2 here, and this will go on carbon number 3 over here, and you will get water. So this is dinitration at a temperature above 60 degrees Celsius, giving you two nitrous groups on the benzene on carbon 1, which you already had, and carbon 3. And this will be called what? 1,3-dinitrobenzene. Clear? Now the mechanism of dinitration, you don't really need to know. You just need to know that for dinitration, mononitration needs to happen first. Once you have the mononitrated compound, then you can make it undergo dinitration. You can't add two nitro groups simultaneously. You will have to have one first, then to that you can add the second one. Therefore, mononitration is done before you could do dinitration. Obviously, you can't simultaneously attach two nitro groups. All right. The mechanism for dinitration, you don't need to know. You just need to know that when the temperature increases, it goes above 60, that's when another nitro group attaches on carbon number 3. Clear? And this is 1,3-dinitrobenzene. Now let's move on to Friedel-Crafts reaction. So we did halogenation. Yes, we did nitration. Let's see the Friedel-Crafts reaction. So we have the third ones, two types of Friedel-Crafts reactions actually. So Friedel-Crafts reaction, you have Friedel-Crafts alkylation, and you have Friedel-Crafts acylation. So you have Friedel-Crafts alkylation, and you have Friedel-Crafts acylation. Now let's see, what do we mean by alkylation and acylation? Alkylation comes from the word alkyl. You'll be attaching the alkyl group, right? So you have C6H6, that is benzene. You will take a halogenoalkane. For example, if you want to attach a methyl group, you can take chloromethane, or you can take anything which will give you the methyl group. So a halogenoalkane will give you an alkyl. So you can take, let's say, RCl. R is the alkyl group. Yeah, that's what you want to substitute on the benzene ring. So C6H5, one hydrogen is lost, and you will have the R group or the alkyl group on the benzene. Yes, and that H that is lost with the Cl minus will become HCl. So your electrophile basically is the R group or the alkyl group. Yes, and what will be the condition? Obviously, this will happen in the presence of a catalyst. Which catalyst will we use? AlCl3 catalyst. For acylation, you will now substitute an acyl group. If you remember, we did acyl chlorides in AS. They were a derivative of carboxylic acid. Remember I told you from carboxylic acid, If you remove the OH, substitute it with a Cl. This will give you acyl chloride. Remember the reaction of carboxylic acid with PCl5, SOCl2. This right here is the acyl chloride or the acyl group. Yes. So, excuse me. So this is what we got to substitute now. Yeah. So you have C6H6. Now, for acyl chloride, again, we will take RCl, where R is the acyl group. And this will become C6H5R plus HCl. Here, the R is the acyl group. Yes, it is not alkyl, it is the acyl group. And what will be your condition? Again, we will require a catalyst for this reaction. So you will require AlCl3 catalyst. Clear? Now, let's see alkylation and acylation. So let's see Friedel-Crafts alkylation. So let's see Friedel-Crafts alkylation. What will be your reagent? So the reagent for Friedel-Crafts alkylation would be, let's take chloroethane. That means which group do you want to attach to the substitute on the benzene ring? Ethyl group. Because from chloroethane you will get ethyl. Yes. What is chloroethane? CH3, CH2, Cl. What will be your electrophile? Your electrophile will be your ethyl group. Yes, which is CH3, CH2. This is your electrophile. Yes, the Cl will be lost and the positive charge will come on the carbon attached to the Cl. Now, what will be your product? Your product will be ethyl benzene because we are attaching the ethyl group. What will be your observation? The observation would be steamy fumes of HCl. So steamy fumes of HCl. And we use a catalyst. Which catalyst is used? AlCl3 catalyst. Excuse me. So we have our benzene ring. This will react. I'm showing the overall reaction first. So this reacts with CH3, CH2Cl in the presence of AlCl3 catalyst will give us ethyl benzene. So the CH2, CH3 will attach here. So this right here is ethyl benzene plus HCl. The H lost and the Cl will make HCl. That'll give you steamy fumes. Yeah. So the first thing we got to do is generate the electrophile. Now, how do we generate the electrophile? Let's see. It'll be in the presence of a catalyst. So you have CH3, CH2, Cl. That's your chloroethane. Yes. This with AlCl3 will give AlCl4 minus plus CH3CH2 plus. Let's see how. So the Cl is more electronegative. It will take both the electrons. Yes. And it takes both the electrons. This breaks. Yeah. Gets a negative charge. This gets a positive charge because it loses an electron. This has a lone pair. It will give the lone pair to aluminum, making AlCl4 minus, and this will break off as the electrophile. Clear? Now we have the electrophile. So there will be step 1 of electrophilic substitution. What is step 1? In step 1, we will have the benzene ring. This benzene ring, along with CH2 plus CH3, this is your ethyl electrophile. You will show an arrow going from the pi ring to the positive electrophile? Yes, making a 4-valent carbocation intermediate. So your CH2, CH3 will attach here. Make sure you attach electrophile, the positive part, to the benzene ring. Don't write CH3, CH2 over here. No, it will be the positive part that attaches to the benzene. Yes, and you have an H here. Then we have step 2. What happens in step 2? You will have CH2, CH3 here, H here. This will be expelled as H plus. You will have Al, Cl4 minus. That H plus with the Cl minus will regenerate AlCl3, making HCl. And what will be our product? Our product will be ethyl benzene. H plus Cl minus will give HCl, and this will give you AlCl3, which is regenerated. So this is regenerated. HCl will give you steamy fumes. And this is your product, which is ethyl benzene. Is this clear? So you get ethyl benzene, steamy fumes of HCl, and you have AlCl3, which is the catalyst, which is regenerated. Clear? Is this understood? And you see, you've put alkyl in place of a hydrogen. You've substituted an alkyl group. We call this Friedel-Crafts alkylation. Is this clear? Now let's see Friedel-Crafts acylation. So we did alkylation. Let's now see Friedel-Crafts acylation. Now we'll be attaching the acyl group. Yes. So let's see what will be our reagent. So I'm taking an example of an acyl group, which is CH3, C double bond O, Cl. Yes. So this right here is your acyl group, as you can see. This is the acyl chloride. Yes. So this is the acyl group. And this is called what? Ethanoyl chloride. What do we call this? Ethanoyl chloride, because you have 2 carbons. So we call this ethanoyl chloride. Now, what will be the electrophile from this ethanoyl chloride? The electrophile will be CH3, CO with a positive charge, because the Cl will break off, obviously. So this is your electrophile. Then what will be your product? So the product for this would be phenylethanone. We will see that. What will be your observation? Your observation would be steamy fumes of HCl. And what will be the catalyst? The catalyst used would be AlCl3. Now we have, let's see the overall reaction. So you have benzene with ethanoyl chloride, which is CH3COCl, in the presence of AlCl3 catalyst, and on one of the hydrogens removed and substituted with this electrophile. So you will have COCH3 attached here. I told you that the positive end of the electrophile is what attaches on the benzene ring. This right here is called phenylethanone. What do we call this? Phenylethanone. It's basically this. C double bond O, CH3. And the H that is lost with this Cl will make HCl. Clear? Now the first thing that we got to do is generate the electrophile. So let's generate the electrophile. How will we generate the electrophile? You will take CH3, C double bond O, Cl plus AlCl3. This will give you AlCl4 minus plus CH3CO plus. Let's see. So this is partial negative, obviously. Bond will break. Both the electrons will go to Cl. Yes, it will get a negative charge. This will get a positive charge. Now, since it has a lone pair, this has a vacant orbital. They'll make a dative bond giving you AlCl4 minus and CH3CO plus, that is the electrophile. You see, you've made the electrophile. Now, once you have the electrophile, what will be the first step? Let's see step number 1. So you will have the benzene ring with the electrophile CH3CO plus. This will make a 4-valent carbocation intermediate where the positive end will attach here. Yes, that's what we have. And you will show an arrow from the pi ring to the partial positive to the positive electrophile. Actually, let me just make it this way so it's easier to show the arrow. So you have C double bond O, CH3. And this right here is your arrow from the pi ring to the electrophile. Yes? Now you've made the 4-valent carbocation intermediate. Let's see step number 2. In step number 2, you will reform the pi ring. So we have COCH3 here, H here. This goes back into the ring along with AlCl4 minus will give you COCH3 here, which is phenyl ethanone. Yes, so you have this C double bond O, CH3 plus AlCl3 is regenerated and you have steamy fumes of HCl. So this right here is phenyl ethanone. Yes, and your catalyst is regenerated and you will have what? Steamy fumes of HCl. Is this clear? Same mechanism. The only thing that's different here is the electrophile, as you can see. Is this? So let's see the last one. So we've done Friedel-Crafts reaction, we've done nitration, halogenation. Now let's see sulfonation. So let's see sulfonation now. The reagent here for sulfonation is SO3, sulfur trioxide, and H2S4. If you remember from O levels, this was oleum. Yes, H2S2O7, oleum. The electrophile that you get from this is SO3. Now you'll be like, this doesn't have a positive charge. I'll just show you. So you have SO3, sulfur bonded via double bonds, 3 bonds, right? 3 oxygens bonded via double bonds with sulfur. Now oxygen, we know, has a partial negative charge. It's more electronegative. And sulfur will have a partial positive charge. Because it has a partial positive charge is why we call it the electrophile. Clear? So you don't necessarily have to make the electrophile here because it's already in the form of an electrophile. So you don't really need to generate it. All right. Let's see the conditions for the reaction. So the conditions for the reaction is that you warm under reflux. So you warm under reflux. What will be your product? Your product would be benzene sulfonic acid. So that's your product. Now let's see the overall reaction. The overall reaction would be benzene reacting with SO3 in the presence of sulfuric acid as catalyst, giving you benzene sulfonic acid. Now, what is benzene sulfonic acid? I'm showing it here because more space. So this is benzene sulfonic acid. The two of the O's stay as it is, and one of them becomes OH. So this right here is benzene sulfonic acid. Clear? Now let's see the steps of electrophilic substitution. Now you don't need to make the electrophile because it's already in the form of electrophile. Yeah, so you don't need to generate it. So first step would be benzene with SO3. Now we know that this SO3 has, so this is partial positive. Yes, so there will be a arrow from within the pi ring to this partial positive sulfur. Now when this happens, sulfur can only make 6 bonds. So if it bonds to the benzene ring, one of these bonds need to break because sulfur cannot have 7 bonds. So let's say these are partial negative, yes? So these are partial negative. Let's say this bond breaks, this one, because one of them is a pi bond. Let's say this one breaks. Clear? You can make any one of them break. That's totally up to you. Now, what will we get? So this is what we get. So you have this benzene with a broken pi ring with a 4-valent carbocation, where you have a hydrogen attached on one end, and you have S, double bond O, single bond O, and this O has gained the electrons, so it will have a lone pair with a negative charge. Yes, so this is what you have. Now, in step 2, this 4-valent carbocation intermediate, so you have this, so you have S, double bond O, single bond O with a negative charge, this along with the hydrogen. So the hydrogen will be expelled as H plus, yes. And what will happen, that H plus will make a bond with this lone pair, a dative bond between this positive hydrogen and the lone pair here. And what will we get? We will get a product which will be benzene sulfonic acid. So you will have S, double bond O, OH. And this right here is benzene sulfonic acid. Clear? So what I'm going to repeat this step 1 and 2. You don't need to generate the electrophile here because the SO3 acts as an electrophile because of the partial positive charge on it. You'll show an arrow from the ring to the partial positive sulfur. Sulfur can make 6 bonds. So you have to remove one of the double bonds, make it into a single bond. Oxygen will gain both the electrons, and this bond, let's say, breaks, and this will get a negative charge. And this makes a 4-valent carbocation, and this attaches to the carbon on the benzene ring. Now this 4-valent carbocation intermediate, H will be expelled as H plus. Electrons go into the ring, as you can see by this arrow. And this H plus will make a dative bond with this lone pair, and it will become OH. And you get benzene sulfonic acid. Is this clear?